So in the previous class, we were going over reciprocal lattices. So as an example, just as a quick reminder of what we did in the previous class, let's say that we had a real space lattice that looked like this, right? And this is just going to be a continuation of these 4 dots everywhere, right? So then we have that this vector is a, to be consistent with last time, let's call this one A2. And this vector right here is A1. And then we have that A1 is equal to A in the X direction. A2 is equal to A in the Y direction. So we wanted to find the reciprocal lattice vectors where the set of wave vectors that is J dotted with AJ is going to be equal to something that goes 2 pi and some integer mj. This pen is not working. Usually make those. Where's Cosmo? What you up to, Cosmo? All right, so we have that as a real space lattice, right? So then we want to find a set of lattice vectors that does that. And if we wanted that to happen, we would need them to be, we could find 2 vectors that do that, and B1 would be equal to 2 pi over A1. And this A is the distance from here to here, right? And here to here, because this is a square lattice. And this would be in the X direction. And then we see that B1 times dotted with A1 gives us 2 pi. And then we can do the same for the other one. And it's just like the previous one. But then this one is in the Y direction. All right. So once we have those 2 vectors like that, we have the real space vectors, we have the reciprocal lattice. What we have then is that we would have a lattice, and maybe this one right here looks exactly like the previous one, except that now you have this vector right here, and this one is B1, and this vector right here, and this one is B2. Where B1, okay, I already written them here, right? That's B1 and B2. So the distance from here to here, the distance is 2 pi over A. And the distance from here to here is just A. So real space, reciprocal space. Questions? So that's the simplest one because it's the square lattice. Then in class last time, I did another one. And let's say that now our vectors were going to be, one is here, 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 here. So if we do that, this is A1. And this is A2, the 2 vectors. And I don't remember exactly. Let me see. I think I picked 2 and 5. Yeah, 5 and 2. So then we would have that A1 is equal to 5A in the X direction. A2 is going to be 2A in the Y direction. with those two guys, I can now write, just like last time, that B1 is equal to 2 pi over 5a in the x direction too. And B2 is equal to 2 pi over 2a. So that's just pi over a in the y direction. So in that case, this is my real space lattice. And I would have a lattice B1 is 2/5, right? So this one is here. And then the other one is here. So this direction is B1. This direction is B2. Vector right here. And then you can see that this distance, well, it's not to scale between the two, but the longer distance, A1, the longer vector A1 has a smaller reciprocal vector in the same direction. And that's because between this one and this one, you get to 2 pi. Between this one and this one, you get to 2 pi. So those are your lattice vectors. Those are your reciprocal lattice vectors. So you have the real space, reciprocal space. So what we have here then is that if I have a squared lattice, I get a squared lattice back. If I have a rectangular lattice, I get a rectangular lattice back, but is rotated, right? So the long axis on the real space is the short axis in the reciprocal space. Yeah. No, here B1 is smaller, right? Because this is 2/5 and this is 1. Yeah. So this one is smaller because this one was bigger. So if I have a real space lattice that is a square, I get a square reciprocal lattice. If I have a rectangular, I get a rectangular reciprocal lattice. Make sense? All right, let me do another example. So this one is a little bit more complicated. In this case, I'm gonna do graphene because graphene is the coolest material ever. You guys knew that already, right? Why are you saying no, Nikita? No, I'm just kidding. It's not the coolest material ever. It's close to. So if I have a lattice, let me use 2 colors to be fancy. All right, so this is kind of like my graphene lattice. You can see it because it looks like this, like this, like this, like this, like this, like this, like this. And there's more atoms attached to it, right? So this is the graphene lattice. This is, all of the atoms are the same. They're just green and blue, but they're all carbon atoms. If you have hexagonal boron nitride, then you would have that one, the blue ones could be boron, the green ones could be nitrogen, or the other way around. So that's a material too. Hexagonal boron nitride looks the same as graphene, except that now you have 2 elements in there, and they go 1, 1, 1, 1, 1, 1, like that. So if we do that, I could set up my 2 vectors, the lattice vectors, and I could have them here. And my lattice is the one that goes from here to there, So now this is supposed to be symmetric, but it's not, and that's my fault. So I could say this is A1, and this one right here is A2. Okay, so it goes, the lattice I'm gonna pick, remember I have whatever I want to pick it. I could pick it from the center of the hexagon, but I'm just gonna pick that my lattice are those green dots. So if I go A1 twice, I get to this point. If I go A1 and then A2, I get to this point. So the combinations A1, A2 let me get to any of the green dots. So that's my lattice. So if we pick those as my lattice vectors, I get A1 to be now this is graphene, right? So it's A over 2, 3, and then a square root of 3 in vector form. And A2, salute. Oh wait, that was not a sneeze. It's like that. So here, A, because this is graphene, A is a distance, and it's the distance between the atoms, and it's about 1.42 Armstrongs. So if this is hexagonal boron nitride, this number is a little bit different, but it's close enough. Questions? So A is the distance. This one is 3 in the x direction, square root of 3 up. This one is 3 in the x direction, square root of 3 down. And those are my two vectors. Again, I could have picked other vectors, right? I could have picked one that goes from here to here instead of one of these two. And with those two vectors, I can do the same. I could expand how to travel from one point to another. Make sense? I just picked these two because they're symmetric. And because they're symmetric, the next step is easier. So now I want to do this, find these vectors, in this case, A1 and A2, there's two of them, and I want to find my B1 and B2, so that when I multiply those two vectors dotted with AJ, I would get 2 pi. So I can do that. And the two vectors that do this would be, I already did it beforehand, is 2 pi over 3a 1 square root of 3. And I have the B2 right here, and it's also going to be 2 pi over 3a. That one is 1 negative square root of 3. Questions? So you can check if A1 and B2 end up being 2 pi, right? So you have to have this 2 pi, then you multiply this 3 with this 1, you multiply this square root of 3 with this square root of 3. You get 3. You add those things together, and you're going to get 3a. And the 2's that cancel and all of that. So yeah. Questions?
So, in the first equation, like describing this stuff, the G vector is just like all these B vectors?
All of the combinations of vectors. Yeah. Just like if you grab R, so we have that. Let me write this down. R, this big vector R, right, could be N1, A1 plus N2, A2. And it can take you to any point in your lattice. Then we have the G. Is the same kind of monster where you can have, let me call this one's M's, B1, so this M1 and M2 are integers, and it could take me to any point in my square lattice in the reciprocal space. So it's the same thing. So now I have my A1, A2, B1, B2. And if I do B2 times A1, I should get 0. And you see that you will get a 3 right here, minus the square root of 3 squared. So you get 0. Same thing here, right? But when I do these two together, you get the negative and the negative. All right. So any questions after this? No? So now that I have these vectors, I actually can draw. So remember, this is in reciprocal space, not in real space. So this is my kx axis. This is my wave vector axis. And this is the ky axis. Like this. I have a point right here in the middle, right? That's my 0, 0 in reciprocal space, right? So if I have that one, I'm gonna put B1 right here. This is B1. And then this one going down here is B2. Okay, questions at this point? They're symmetric again. So this is the two vectors, B1 and B2. So let me grab these two guys and complete the unit cell. So over here, this is my unit cell, right? At this point, I just took this vector, put it up here, this vector, put it down here, and you see this is my unit cell. If I do the same thing, you'll see that there's 4 points, the same thing, like this, and like that. So that's also my unit cell. So this is my unit cell in real space. This is my unit cell in wave vector reciprocal space. Questions? No questions? All right. So no, this one works. So I think that the 3's cancel out if you do this.
Yeah, the 3, yeah.
So when I did the math, this worked. Maybe you want to do the math?
Because we can have it be any multiple of 2 pi, right?
Right, any multiple.
And so, like, yeah, we could do that, but pi is also just a multiple of 2 pi, so.
So yeah, I think that this works. Maybe I wasn't right and I missed a factor of 2.
I mean, yeah, it's not a big deal, but I'm just saying, like, if my calculation is wrong, or like it should be.
I think this one works, but I'm not sure. Maybe if you want to double check, but it doesn't really matter. Like Casper is saying, you just multiply by an integer and you get the 2 pi, right? And so forth. All right, so this is the another thing, reminder of what we did last class, a few classes back. So how do I do it? All right, so let me copy what I had up here. So now it's not right. Like this. Then I'll get the green ones here. Then I get the blue ones here. Green ones, and one last blue one. All right, so I don't know if you can tell there's blue and green. It's hard to tell because the projector doesn't give you the right color. But I said that my lattice goes from here to here to here. This is my lattice, right? Like the green ones. So we built the Wigner size cell. And what we did is that, let's say I took this guy as my center point, and I started making, so between this point and this point, there's a halfway point. And I draw a line through that halfway point. That halfway point is gonna take me through here. So now if I do it between this one and this one, right? This two, I draw it, and I think that my halfway point takes me through here. So this is the line halfway between those two. If I do the same, I saw this two, and I think that my halfway point between those two is gonna take me through here. No, it's kind of crooked. It's more like this, right? And then the halfway point between these two, this one and this one, is through here. The halfway point between these two is kind of like through here. The halfway point between these two is kind of like through here. So you have to do this in dotted paper so you get it right. But you can see that the Wigner size cell of this lattice is this little hexagon, right? So this is by convention a unit cell. This would be the smallest unit cell. It's not the only, but by building it like this, passing through the halfway lines between dots, now I have constructed it that way. And this is the same actually as that one up there in area, or if it was three-dimensional, in volume. The one up there is not constructed like this. It's just by looking at it and saying like, okay, this tiles the whole thing. So I have two different ones, but this one here, you can tell this is hexagonal because it's a little hexagon. And if you put the hexagons together, you can tile the whole thing. So this guy right here, the green one, is the center of the hexagon. Whereas up there, we have that little rhombus, and the green ones are at the corner of the rhombus. Questions? All right, so that's how I built this one. This is in real space. So now we have this one. And let me redraw it over here. I have this point. Then if I go B1, I'll go over here. If I go B1, B2, I have over here. If I go in the, and add the two together, right? B1 plus B2, I would get a point over here. Does that make sense what I'm doing right here? If I keep going, negative B1 is probably gonna be over here. Negative B2 is probably gonna be over here. Negative B1 minus B2 is probably gonna be over here and such. So now you see what I have. Those are points. So these guys are in real space. And these guys are my reciprocal space lattice. So in real space, we get a hexagon. What will we get if we start putting points midway through those guys? So let me start over here. So that's probably around here. If I go through here, that's probably around there. If I go between those two, that's probably around there. If I go around this two, that's probably around here. between these two, that's probably around here. Between these two, that's probably around here. Oh, did I miss anything? No. So if I was a 5-year-old and I told you, look, I drew a hexagon, you would believe me, right? It's not symmetric because I'm not being careful with it, but you can see the hexagon there, right? So the real space lattice of the hexagonal lattice, it's a hexagon. And if we take that same lattice in reciprocals and look for its reciprocal space partner, we see that it's also a hexagon. Main difference though, the flat parts over here, which were in the y-axis, the flat parts are in the x-axis. So again, we had the square lattice, the reciprocal of it was a square. We had the rectangular lattice where the rectangle was going along the x direction. In the reciprocal lattice, the rectangle is gonna go in the y direction. Here we have a hexagonal lattice. The flat parts are in the y-axis. Here, the flat parts are in the x-axis. So it's just a rotated hexagon. Make sense? Questions? No, we're good. So you can do this with all of the lattice that you want. This one right here, like I told you before, is the Wigner size lattice or Wigner size cell. That one right there, that's the Wigner size cell. So this is a unit cell right here. Cosmo, is that one a unit cell up there? Yeah, the rhombus, is that a unit cell? Yes, right? In real space. So unit cell right here, unit cell up there. So this is a unit cell. This is a unit cell. We constructed it by putting together dots together, the distance between the points in the lattice. So we have the Wigner size cell. That's the construction that we just did. We can do the same for these guys. This is a unit cell too, right? In reciprocal space. And this is the reciprocal space lattice this is for the reciprocal space lattice. This guy right here is also done by the Wigner size construction, but when it's in reciprocal space, it's not called the same. Reciprocal space, this is called the first Brillouin zone. But it's constructed the same way from constructing the Wigner size lattice. It's just that it has a different name because we have to be fancy, right? So the Wigner size construction on the reciprocal space is known as the first Brillouin zone. And it turns out that this first Brillouin zone is really important. You probably heard about it a lot. If you go to a condensed matter seminar, it's probably always going to be said in those. Why is it so important? Anybody knows? So if you look at the first Brillouin zone, it's actually the when you're measuring things on them, you can relate it to where in the first Brillouin zone did you measure them. So this is a 2-dimensional thing, but it's also existing in 3-dimensional lattice. And it would be like a little cube, right? If you had a cubic cell in real space, you would have a little cube cell in reciprocal space. So this one right here, the first Brillouin zone, right here, is gonna tell you all the information you need for electronic structure of the system, for how the phonon modes appear in the system and so forth. So all of that information is put in this first Brillouin zone. Okay? So now let's figure out what this is. So again, this is the hardest part of condensed matter, learning what the lingo is. What are the things that we're talking about when you're talking about? It's kind of like in particle physics, right? Like we have the standard model and everybody talks about the standard model. But what is it? You have to take a class on it. You don't learn that in the seminars. So this is where we learn about this guy. So let's see. We have this first Brillouin zone. So let me come back to this one in a little bit. So let's say that I had in one dimension, actually, this lattice right here. So this is one dimensional, right? What is the spacing that I have? A. It's just one number. The size of A might be the distance between these two. Let's assume they were atoms. So this is one dimensional in real space. But just like we did before, we can generalize it to one dimension and find the reciprocal space lattice. What would be the reciprocal space lattice? Well, here we will have another set of points right here. This is my reciprocal space lattice. Make sense? So Paul, if the distance between those two guys is A, what is the distance between those two guys? 2 pi over A. Perfect. Okay. So in one dimension, you could also say that this is A in the X direction, and this is 2 pi in the X direction. Mm-hmm. Yeah, it's just a line. So with that, let's say that what we were going to solve is that these guys, okay, so these guys right here are atoms. And these atoms are going to make such that you have a potential this is your X direction. And your potential is going to be such that we have an attractive potential with a distance A between them. And this attractive potential, I'm not going to solve it, but you can solve it analytically if they're delta functions. If they're, let's say it was a Coulomb attraction, and you were trying to figure out how an electron gets attracted by the chain of atoms, right? The atoms attract their ions, so they're attractive. They want the electron to come in, so they will have this, but now being Coulombic attraction. And so the electron likes to be here, or here, or here, and we would solve the quantum mechanical problem. So if we do that, and again, this distance right here is A. If we do that, we actually would be solving for the electronic states of this thing. And we would have something that as a function of energy right here, this would be kx in this axis. And because of the attractive interaction, is going to go like this. Okay. and in this direction like this. And then here, so this is this distance was A. In K-space, what is this distance? Right here. It's actually pi over A. So that distance right here is the same one as up here. So this distance from here to here is, this is 0. This is 2 pi over A, negative pi over A. Does that make sense? So this is negative pi over A. This is pi over A. And then it would continue in this direction like this. And this is symmetric again until it reaches that point. And this is 2 pi over A. Just like that. And it continues in all directions. This was periodic, so I can take this and put it here. I can take this and put it here, and so forth. And we already did this before, right? So I could rewrite it as this is my energy. This right here is Kx. This is 0, pi over A, negative pi over A. And you have those bands. So that's the band structure in one dimension. So this is the band structure in for this one-dimensional problem. There's a states up to this energy, then there's a band gap. There's a state up to this energy, then there's a band gap, and so forth. Questions? No? Yeah? Anybody? We're good? All right, so this is in one dimension, right? And I can have a band structure right here. So let me go back to graphene. So this guy is the same thing I'm gonna redraw, but do it carefully. So we have this guy is in Ky, Kx, right? And then on top of this, I'm gonna draw this first Brillouin zone. So let me do that. This is Kx, this is Ky direction. So my two vectors are B1 and B2 right here, right? So let me write those down. So this one was 2 pi over 3a, 1 and the square root of 3, and B2 was 2 pi over 3a, 1 minus the square root of 3. So carefully That's 1. Well, let me make it a little bit longer. That's 1. So I have to reach probably down to here, and that's the other. Okay. So this is the 0, 0 point. This is the location of another point. This is the location of another point. There's another point over here, right? In reciprocal space. Those are identical points because they're periodic, right? And then the other thing that I had is that I'm gonna draw the reciprocal lattice here. So let's see if I can do this better than a 5-year-old. Probably not. Yep, it's not symmetric again, but you get the idea, right? So if I know that that one is 2 pi over 3a, 1 is square root of 3, this is the same thing, but negative square root of 3, I can figure out what this point is, for instance, right? And all of those points, actually. The most important point, actually, for graphene. So yeah, I knew I was going to mess it up. So this is supposed to pass through the middle of this line. If it was symmetric and I was doing it carefully, like probably with a drawing program or drawing it with a ruler and measuring things, this line right here would be intersecting the middle of this one. Does that make sense? And it would be symmetric, right? So it turns out that notation-wise, we have a specific points. So this is the gamma point. So gamma is at 0, 0. That's where the center of our lattice is. And this is the first Brillouin zone, has symmetry points that are really important. So for instance, this right here is called the endpoint. And I have no clue why they get their names, okay? It's just that everybody uses those names. So the endpoint would be halfway out. If you added B1 and B2 together, halfway there, right? So it would be like 2 pi. So pi over 3a, I think. That's the endpoint. So this is a symmetric, an important symmetry point, because this point, this point, this point, this point, and this point, they're all identical. That's the symmetry of the system. So all of the middle of the hexagons are symmetric in a symmetric hexagon. Questions? No? All right, so then there's another point of symmetry here and here. For graphene and this lattice, well, for this lattice, this is called the K point right here. K, capital K. So for instance, if I have this, this is a vector, right? By my notation, this K point is happening at 2 pi over A, 3 pi over 3A, sorry, because of this 3. 2 pi over 3 square root of 3A. Okay. So that's my symmetry point, because there's a lot of points that are the same. And then in graphene, this one is called so the corners would be called the K points, but it turns out because graphene has 2 atoms, these 2 are not exactly identical. So this one is also 2 pi, located at 2 pi 3a, and then here is minus 2 pi 3 square root of 3a. Okay, does it make sense up to this point? We're all good? Questions? All right, so these are crystallographic directions. And it turns out that in graphene, these K points are really important because that's where interesting things happen. So if you were to solve the problem, just like we did here, but instead of being in a one-dimensional lattice, it was in this two-dimensional lattice where the atoms are talking to each other. There's that same periodicity and all of that, right? In this point, this point, this point, you can solve what are the bands, the energy as a function of position in K gonna look like. Does that make sense? Just like we did here, where is it? So this is my, as a function of Kx, this is the energy, and it's the same over here, right? Does it make sense? All right. So if we did the same thing for graphene, let's go. So I could draw this in 3 dimensions if I was Leonardo da Vinci, but I can't. I can barely draw in 1 dimension. So let's say that we were going from in Kx space. So this is the energy. This is Kx. Okay? So we're taking this route from here to here. Okay? So this is at the gamma point, and this right here is going to be the M point in this system. If I were to do that, my band would look like this. That's the first band. And then on the top, it would look like that. Okay? Does that make sense? And then this is symmetric, right? So if I go from gamma point to this other side, it's also M. M. And it looks the same. So I would have that it looks like this. And then here, it would look like that. Okay, questions? No? We're good? So I can draw the same thing for graphene. This is not going to be easy to define as the Kx or Ky direction. So for instance, if I go from this point to this point, right? It's not in the Kx axis because it's not in this axis. It's also not in the Ky axis. Actually, I could draw it from this point to this point and it's all in the Ky axis. But let's assume I was staying here. So this is again my energy. And this is in K space. So I'm gonna draw it here is my K point. And I'm gonna go kind of like this. Okay, so I'm going from K to gamma. So this is 0, 0. This is at 2 pi 3a in the x direction, 2 pi over 3 square root of 3a in the y direction. Okay? And then I could go in the other direction. So if this is k prime, this one is also k. This one is k prime, k prime. So I can go from here to here. So you see, this is how I know that it's not symmetric, because these two lines should have been like a straight line. Let's assume that here is my K prime point. And now I'm gonna try to do the energy there, okay? So actually this is at the gamma point, so it's the same energy as before. So it's gonna start there. And then this point over here is supposed to be the same because it's the gamma point, so the energy is the same at this point, right? So now instead of going in this direction, I'm going in this direction. If we do this, it looks like this and like this, and like that. All right, so let's look at the difference, right? Here we see a band gap. Here, this valence band and this conduction band are touching. What does that tell you? That you have a conductor, exactly. So in this direction is a semiconductor. Here's the only point that is interesting. In this direction, the two bands are touching, so there's no band gap. But they're also going to zero. So it's conducting because there's no band gap, but it's also not fully a metal because there's nobody here to conduct, even though it's a conductor. So if it was perfect, it would be like almost a metal, but not really. Okay, so those are subtleties. Metals would have some states here that are ready to conduct, but this graphene does not. So now these things are periodic, right? So whatever is at this point is repeating from the previous point. So this guy comes like this, and this guy comes out like that. Do you guys see that? Just from the periodicity? So Cosmo, what does this look like? Like a what, sorry? A lemon? All right, let's zoom in through here. So this is how you zoom in, right? What does it look like? So yeah, cross. But remember that this is like this and like this, right? Because of the periodicity. And then this one is going, this one and this one are like this. Would you say those look like two cones?
Yeah.
Because they're rotated, right? So if we zoom at this point, exactly, two cones touching each other like this. So if we come to this point right here is what we're zooming in. So this, at the K points, you get two cones connected to each other. Does that make sense? That it looks like two cones? And that we have, as a function of energy, there's a states all of the energies, but then they're going down to these little points in cones. Does that make sense? All right, so going back over here, let me just bring this over here again. When we look at the almost free particle in that periodic potential, we were saying that it behaves almost, and you see this roundiness here, but you see here is like a free particle. So in this region, it's like energy is proportional to h bar squared over 2m times momentum squared, right? That was what we said before. So this makes it obvious, right? It's a parabolic. So this is called Schrödinger-like. because of Schrodinger equation. Now let's come over here. We have here, this is, again, this is direction in momentum, in wave vector momentum. This is direction of energy. So what does my energy look as a function of momentum? Yeah. Yeah, so if I were to ask you, what does the momentum, what does the energy look like as a function of momentum? What would you say? Is there a quadratic dependence on the wave vector? What is it? Yeah, but how does it depend? Is it cubic, quadratic, linear? Linear. Yeah. So you see it's a line, right? Yep. So it's actually linear. And this is linear. And it turns out to be Fermi velocity times the value here of the wave vector. So it's linear in K. So let me rewrite it. Energy is linear. It's almost equal to, so there's actually a plus minus Fermi velocity, which is a number, times the whatever wave vector you have. So here, the particles have that as you increase in energy, as you increase in K, is increasing in energy, so it takes the positive side. And the slope is actually given by this value, which is actually the Fermi velocity. So this is a number, and this is your value of K, and you see that they multiply together to give you the line for the energy around this point. And over here, as your momentum increases, your wave vector increases, your energy is coming down, so this is the negative side. Yeah?
Does this approximation tend to hold true across all materials, or
No, just graphene. Yeah, just graphene and just around these points. Because over here it's not linear, right? Over here is not linear. Over here is lemon-like. Does that make sense?
Yeah.
So it's just here, right? But it turns out that this right here is where electrons like to live when you have graphene right here. And they have that the energy of the electrons is linear with the momentum of the vectors. All right. So does that make sense? Why is this important? Because most systems that we know of, the energy is proportional to the square of the wave vector. Here, the energy is proportional to a number, a speed, times wave vector. This is what relativistic particles do. So this is Dirac-like relativistic physics. This is Schrodinger, normal Schrodinger equation physics. So graphene is the material that has this property. So everybody got really excited in 2004. So in 2003, it got discovered, but they didn't realize this. The guys who did the experiment didn't realize that they had just discovered a system where the particles behave. So this right here is the energy, for instance, of particles traveling at the speed of light, where this would be the speed of light. That's the momentum of, that would become the momentum of the photons, let's say. Or more interesting even, neutrinos. So neutrinos that are traveling close to the speed of light have this energy versus wave vector relationship. So these guys didn't realize they had this when they did the experiment, but a year later, everybody knew about it because actually this was predicted back in the 40s. So the first prediction happened in the 40s. Somebody solved how do electrons travel inside of graphene. They had, this is where in graphite, right? This is how the atoms of carbon gold look like. They started looking at this, they figure out what is the wave vectors that I want to put in my unit cell. Then they assume an electron can hop from the green to the blue, green to the blue, and they come up with these pictures, all of these pictures that we just did. The only thing I didn't show you is how to solve that the electrons are hopping from left to right, but it's just solving the Schrodinger equation like in this system, right? So the electrons are hopping from not red, sorry, from green to blue as the atoms, just as like they could hop from this point to this point in this linear chain of atoms. Here they can jump in this gigantic flake that we would simulate, and we would come up with this energy versus wave vector. And it looks different as you go in this direction than in this direction, but in this direction, it has that property that you have Dirac cones. So once you have the Dirac cones, people got really interested in graphene because they saw that these electrons inside of graphene behave like, for instance, photons traveling in space or neutrinos traveling almost at the speed of light. The only difference is that this is not the speed of light. This is like 100 times slower than the speed of light because electrons don't travel super fast, right? They travel fast, but not at speed of light fast. So this was discovered in 1947 by a guy named Wallace. Then actually other people discovered it over time. In the 70s, I went to the University of Texas at El Paso. That's my undergraduate institution. And there's a faculty member there that did the same discovery in the 70s. And then in around the 90s, Dr. Mintmeier did the same discovery. So I don't know if you guys remember Mintmeier. No? He retired recently. You seen him around? No? Okay, so he used to be our colleague here, used to be department head. So in 2012, he hired me, so he was a department head when I was hired. So Mintmeier discovered the same thing in the 90s. Like nobody remember that other people discovered it. So you discover something and then it just gets forgotten. How sad, right? But that's how it happened. So in the 90s, Mintmeier comes up with this, and guess what happens too? People discover carbon nanotubes in a lab. So at this point, this discovery by Mintmeier that other people had done before, but he didn't know about it, comes back up in an experiment. So the theory that showed this was done by several people independently. And then Smalley at Rice University finds carbon nanotubes in his buckyballs. So you guys know about the buckyballs? No? Smalley is a person, he was a faculty professor at the University of Rice. And he and other people theorized, or were thinking, hypothesized, not theorized, but hypothesized that in space, you could have like huge chunks of current flowing out of the plasma. It would hit carbon atoms and they could form different structures. So he started doing in the lab that where he would put like an arc near gas that had hydrogen and carbons compounds, or even in suits made out of carbon, like the thing that you pop out of your kitchen or coal furnace or whatever you want, right? So they would put a huge current and then look what's inside of this. And they found that they had these buckyballs, and they're called buckyballs because there was a fellow, his name is Buckminster, that came out with these geodesic dorms that are made out of hexagon and pentagons. And those are called buckyballs, kind of like a soccer ball. But now imagine that each of the vertices is a carbon atom. So Smalley came out with carbon-60 and realized that he had carbon-60 when he ran this kind of like currents, super high currents through an arc, and it made the carbons form into this new shape. So carbon-60 is one of the shapes. The other one is nanotubes. So carbon nanotubes are graphene, the graphene, imagine that you roll it up. Or imagine that you have a carbon nanotube, you cut it in half through the axis and it rolls out and it's graphene. So it's the same thing. So when Mintmeier discovered this, publishes it, Smalley just publishes carbon nanotubes exist and here's proof of them. And then in 2004, people are rediscovering that they would have these really cool properties because they would behave like relativistic particles. So that's the way science goes. Questions? So the reason I knew that this guy at UTEP also discovered them is because my university had a Smalley go to give a seminar in our department, in our university. And Smalley's like super famous for discovering the buckyballs, right? And that's where they said like, oh, I didn't know this, but in 1970, so-and-so, your colleague right here discovered this. So I wouldn't have known because the guy was very humble and would never say that he did that. All right, so that's for graphene. Let's see, what else do I want to cover? We have first Brillouin zones, which is how you build a Wigner size cell, but in momentum space. I showed you that the square lattice in real space has a square lattice in your momentum space. The rectangular looks like a rectangle, but it's rotated. I showed you that the hexagonal looks like a hexagon too, but it's rotated too, right? So not all of them are going to be one-to-one like that. In fact, the FCC lattice, the phase center cubic lattice that you would come up with by building, if you did the Wigner size cell of the FCC lattice, and you go and do the same thing and figure out what the first Brillouin zone, what it looks like. And remember, this is three-dimensional, so it's not like a flat thing like this, but it's actually a geometric solid, right? So for instance, the cubic one would have a little cube. If you take the FCC one, it would look like a BCC lattice in reciprocal space. So it doesn't look like a little FCC lattice. It looks like the body center cubic. And if you take the body center cubic, it looks like the FCC lattice in reciprocal space. So they're not one-to-one the same thing. So that's, I have just shown you the two-dimensional cases, but they're very similar things in 3 dimensions. And you would have a volume about those. All right, so I have a little bit of time. I was hoping that we would be able to look at some of the homework problems, but we only have very little time. So let me just then finish the chapter and cover the last thing of importance in this chapter. And then next class, you guys get to show what you did and your homework if you want, okay? Those are for your presentation points. So let's say that I had a lattice that looked like this. Again, two-dimensional, because that's what I know how to draw. So it's not a square lattice, right? So it has like a tilt to it. Let's say that this was my lattice. So this point right here is 0, 0 in my two-dimensional lattice. I'm designating that one as my 0, 0 point. I'm going to say that this one is A2. And this one is A1. And it's supposed to be tiling periodically what we have here. Questions? at this point? About this lattice? All right, so now what I need to do is define a new thing. To define this new thing, I have these vectors A1 and A2, right? So any point in real space can be designated by my A1 and A2. Right? Okay. So what I want to do now is I'm going to have that there's G vectors, and my G vectors are going to have, so here I would put a little n vector that corresponds to n1 and n2. Those are my two integers. So if this was three-dimensional, I would have three vectors right here. So let me give you the three-dimensional vector of the G vector, the notation for it. This is actually K, L, and M. And what that means, this is by notation, people use this notation, is that there's a capital K B1 vector plus a capital L B2 vector plus a capital M B3 vector. So assuming that it was three-dimensional, this is not three-dimensional. So the other thing that you know is that we have that anything that is J dotted with R is gonna give you 2 pi times some integer, right? So at this point, we know that this is true. And this integer could be 0 if the vector that you're picking from G and this guy are 90 degrees from each other, which could happen, right? So now the question is, this guy, if you remember from your math classes, can also, even in 2 dimensions, it could represent a plane. Sorry, in 3 dimensions, you represent a plane. In 2 dimensions, it would represent a line, right? So if I were to put this and give you numbers here, I would have a line in 2 dimensions. And if we're extending this line in 3 dimensions, it's actually a plane. That makes sense? So one question I could ask is, how do I define a plane or a line going through here? Okay? How do I define the planes or the lines in my system? So what I would need would be the following, that there's a J, K, sorry, a G, K, L, M, that when dotted with my R, N1, N2, N3, is gonna give me 2 pi and some integer. Does that make sense? So if I have a line going through here, there's gonna be a vector with K, L, M, N that would tell me what those lines are, so that when I multiply this by this dot products, I get I. So we have in 3 dimensionals a plane that could be depicted. In 2 dimensions, it would be lines. Two pi and some integer psi, whatever integer you want. So for instance, I could make a line going through here, right? So this is a line that I could draw. And for instance, this line passes through this plane too. So there's all of these lines that go like this. Okay? So that line is different from a line that would pass through here, right? And if we have planes, it could be a plane going like this and another plane going like this. So how do I define those lines? If I wanted to tell you this is the line that we're interested in, or this is the line that we're interested in, this is the plane that we're interested in, or this is the plane that we're interested in. So actually those lines or those planes are defined by these values, the K, L, and M values. So let me stop there. And for instance, there could be another line that is passing like this, right? How would we define those lines? So let me stop here, but just tell you that these lines are important. These planes are important because usually when you have a crystal, the crystal is broken or has facets along these lines of the lattice. So for instance, if you look at a diamond, right? The diamond gets cut. How do they cut it? They find the good places where if you go like this to it, it would crack like that. And those facets that you make are planes like that that go and are perfect because the atoms in it are passing through it like this. And you see that the diamond might have a bunch of different facets, right? So those facets are all different planes that you're cutting it from it. So we'll get to that in the next class. And that's it for today, unless you guys have questions. No questions? All right.